For theoretical probability, we needed someone like, I think this is Aragon, Lord of the Rings man, Lego guy with his sword. So let it be. So theoretical probability is also, in some cases, like in our stats class, we call it classical probability, is where the outcomes in a sample space, we know all of them at the very beginning. And this is always all gambling things fall under this. We can list them all very easily. We know them all from the get-go. If we juxtapose this with what we're going to look at in empirical probability, we don't necessarily know all the possible outcomes. They're not as clearly known. So like with raining and not raining sort of thing, those two outcomes we definitely know. That's a 50-50 chance, but that's not exactly how it works, right? Because there's the temperature, there's the wind, there's all kinds of other things that affect how likely those things are to occur. Whereas when we're working, say, with a deck of cards, we know there's 52 cards in that deck. We know every single card. We know every single suit. We know all the things about it. We just don't know if we've carefully shuffled it and everything's randomly there. We don't know what card we're going to pick when we pull it out. We know but we do know the probability. We can calculate it. And that's what we're going to learn about right here. So let's say we flip a coin 100 times. Quick note, the sample space is heads and tails, right? A very clear outcome. If it's a fair coin, we would expect it to land tails up roughly 50 times, right? Because there's only two outcomes and we're flipping it over and over and over. About half the time we expect it to show up as tails because there's only two possible outcomes. If we think about what that percentage is, that's 50 out of 100 flips, which is 50%. Oh, whoops. We were supposed to write that as a fraction. So there is our first probability. Between these two, that's the probability of tails. If we were to write this in probability notation, we would say the probability of this particular outcome, or this event, whichever way you want to think about it, would be 1/2. And generally speaking, the probability of any event E that we want to talk about, we use the capital letter E to represent event, that comes from a sample space, which is all the possible outcomes from an experiment, is just a fraction, which equals the number of outcomes that are in this event divided by the number of outcomes in the sample space. So if we're rolling a die, a 6-sided die, here comes the sample space real fast. 1, 2, 3, 4, 5, 6. If I want to know if the number of outcomes in that sample space is 6, right? There's 6 possible things that could happen. If we're rolling a 2, the number of outcomes in that event is 1. Now, when you write out this work, you do not have to write out all this stuff that I'm doing here. You don't necessarily have to label event E equals this is the sample space of event E. This is the sample space of the probability experiment. Here's the number of outcomes. I'm just wanting to write this out nice and carefully so you can see where this 1/6 comes from. And then because we can think about probabilities as fractions, decimals, or percents, we can smash this in a calculator and we can say, oh, what is 1 divided by 6? It's 0.166666, blah, 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 blah. So that's about 0.17. Turn that into a percentage, that's about 17%. So when you roll a 6-sided die, 17% of the time approximately, you're going to get a 2, assuming it's a fair die. All right, let's try another one. What about rolling a number less than 5? Well, again, it might be helpful to list our sample space. Okay, so these are all the options for this experiment. Our event for E, which is less than 5, we need to think about what are all the numbers, what are all the possibilities of a thing less than 5. It's these things. So what counts as meeting this criteria is 1, 2, 3, 4. My number of outcomes in event E is 4. My number of outcomes in the sample space is 6. I was about to say 5. So the probability of rolling a number less than 5, this is one way to write it, is equal to 4 out of 6. Now, you may note that 4 and 6 are both divisible by 2, so we could write that as 2 out of 3. Wonderful. It doesn't particularly matter in my mind whether you do it, which way you do that. We could also take 2 and divide it by 3, and you could get, oh, it's 0.66666 forever repeating. So that's approximately 0.67, which is 67%. So again, we could say 67% of the time when rolling a single die, you're going to get a number less than 5. How about rolling an odd number? Well, that event, we already listed it before, is 1, 3, 5. There are 3 numbers in this event, so if I wrote how many outcomes are event E, what's that count? It's 3. We still know the number of outcomes in the sample space is 6. So the probability of rolling an odd number is equal to 3 out of 6, or half of the numbers are this, which is exactly 0.5, or 50%. That is probability in a nutshell. It can get super complicated very quickly, but it's the basics of it. Number of outcomes in the event divided by the number of outcomes in the sample space calculates your probability. Note that the key here is being able to count how many things are in the sample space and how many things are in the event of interest. And these two things can themselves be quite complicated. Check out number 15. We're going to flip 3 of these coins and record the result of the 3 flips, and that's going to be our probability. So I'm going to start with, if I flipped all 3 coins heads, we could get HHH, and then I'll try to systematically list out the rest. HHT, HTH, THH. Let's see, then it could be HTT, and then THT, and then TTH, 1, 2, 3, 4, 5, 6, 7, and then finally TTT. There are other strategies for ways to list this out. Note, though, maybe the most important part here is that the sample space of flipping 3 coins is equal to, or the size of the sample space, is another way to talk about the number of outcomes in the sample space, is 8. Okay, so then we're calculating some probabilities. What's the probability we get 2 tails? So having this listed here is going to help us identify that event. So 2 tails, I think what we need to note here is that means exactly 2. So it's this outcome, and this outcome. So the number of outcomes in this event is just 3. I'm going to say 2 T's here as my probability, and that's going to equal 3 out of 8. Now, at least 1 tail is a little trickier. Maybe. That means 1 or more. So this has at least 1, 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 and this has at least 1. Note that the number of outcomes in that event is 7. So our probability here is 7 out of 8. And at this point, I'm not bothering to give us decimals. I hope that's okay, or fractions. And then our last one, at most one tail. This is one or less, right? We can't have any more than one. So going back to our sample space, it could be this one, this one, this one, or heads. We could have no tails in there for at most one. So that was 4 outcomes for that event. And so our probability for this is 4 out of 8.